All right, what we discussed last time was we talked about how the scientific method is just an extension of the problem-solving process. The purpose of doing the problem-solving process and then working in the scientific method is that the scientific method is a set of rules that are added on to the problem-solving process to give it a little bit of reliability. Again, we talked about it should be repeatable, should be something where you have just generally have the ability to observe what's going on in there. The scientific method, if you don't observe something or if you can't measure something, you can't prove that it actually happened. So what we're going to be focusing on today is the second element of the problem-solving process, which is understanding what makes a good solution. Okay? So with our 5 steps of the problem-solving process, step 1, make an observation. Step 2, questions and performing initial research. Step 3, formulating a hypothesis. Step 4, performing an experiment. Step 5, evaluating the hypothesis. We're going to particularly focus on this area right here, which correlates with the hypothesis. Okay, what is a hypothesis? Yeah.
It's basically an educated guess as to something that could come as a result based on the findings of many different observations.
Right, it's taking your observation and it's trying to figure out a way to explain it using what you know. So having this hypothesis and the idea of what we're dealing with a hypothesis, how do we know what makes a good hypothesis? What's the difference between a good hypothesis and a bad hypothesis? Yeah. Whether or not it makes logical sense. Yeah, if my hypothesis is, let's say I am measuring the solar radiation and I see variations in solar radiation and I say it's because Thor is fighting somebody on a different planet. Like that probably doesn't make logical sense.
It is a hypothesis though.
It is a hypothesis. But that said, it may not make logical sense. Yeah.
Testable.
Something that's testable, something that is measurable, something that is observable. All of that is very important. What I'm going to introduce to you today is kind of the meat of what makes a good hypothesis. And I'm going to use none of the words involved in hypothesis. Okay? Today we're going to be talking about, see how far this direction I can go. Variables. Does anybody know what that word means? You know what that word means?
Well, I mean in the sense of something that can be changed, like something dependent.
A dependent variable is a type of variable. You're getting ahead of me now. What is a variable as a whole, though? It can be changed. Okay. What else?
There are factors that go into different processes, whether it be an experiment or, in this example, a hypothesis. What are the different variables that belong to your hypothesis? The sun, the radiation, the earth, air quality, whatever.
I'm going to go ahead and give you an even more general definition. That was really good. I'm going to give you a more general definition. A variable is anything that can be measured. I think we talked last time about how an observation, somebody mentioned that an observation is something that you sense, you see, you feel, you experience. But in reality, an observation is something that gets measured, even if it is by your body's senses, your body's sensory systems. It is a measurement that we're taking. A variable is anything that can be measured. Okay? Now that's going to open it up to anything that can be measured. You can measure qualitatively on a scale of 1 to 10, you can measure how happy you are. You can measure how much stress you're in. You can measure how much radiation you're incurring. You can measure how much sunlight you're receiving. You can measure your own surface area. You can measure how much keratin is in your body. You can measure all of these different things. You can measure an infinite amount of things. Anything that can be measured can be a variable. Now, with that said, not every variable is relevant to everything. In the scientific community, variables are very critical because if you don't understand your variables, you will never have a good hypothesis. Good hypotheses, ones that make sense, account for all of the relevant variables. Okay? If you don't account for your variables in your hypothesis is trash. That's kind of what you were getting into, Jeremy. It has to be testable. Well, it has to be testable. You have to understand what variables you're testing. You have to understand what things you're changing. It has to be realistic in that you have to understand how closely tied those variables are to your hypothesis itself. So there are 4 different kinds of variables. Jace, you already mentioned one. The first kind, we'll go ahead and start with that one, is the dependent variable. Anybody know what that is? Yeah.
The dependent variable is a variable that changes depending on the results or depending on the independent variable, which is a set number or measurement.
A dependent variable is also something you can write off on your taxes. You know, the 8 o'clock class did not laugh at that joke, and it broke my heart. I love that joke. It's too early in the morning for tax jokes. This can be considered to be the output of a system. Okay? When you have a dependent variable, this is what is changing that you cannot directly control. If we're doing an experiment on materials that are being used in a space shuttle, and we want to know all the properties of that material, there are certain things that we can't directly control. We cannot directly control the strength of the material. We can't control what its heat dissipation is. We can't control what its fatigue resistance is. We can't control what its electrical conductivity is. We can't control what its radiation resistivity is. Those are things we can't control. But those are things that we can measure. And there are things that may be important to the function of the device. Okay? So that's why this is considered to be an output. It's something that is important that you want to measure, but you can't directly change. As for dependent variables, you can have as many dependent variables as you want. You can measure anything on here. Measure how it changes. Hurts none. Plenty of scientists will have dependent variables that they witness change. They'll just capture as many as they can. They'll discuss how those variables are changing. They'll collect mountains of data. They'll publish the data online because, quite frankly, they have more data than they know how to use. Okay? So, in connection with the dependent variable, you have the independent variable. What is the independent variable? Back of the room.
It's what the person doing the experiment controls.
This is the directly controlled by the researcher quantity. Okay? This is if we're dealing with material and we're trying to see what the material properties on a spaceship. This could be the chemical composition of whatever component we're using. This could be the amount of force that's being transmitted when we're testing it. This could be the temperature of the component or of the environment when they're testing it. This could be the amount of radiation in the room. You increase the radiation, you decrease the radiation. This is something that you can change this as much as you want. You want to know what the dependent variable does in relation to changing the independent variable. Another example I like to use is, let's say you're trying to determine how a plant grows based on how much you water it. Okay? So your independent variable here would be, well, how much you water it. You vary how much is watered. And the dependent variable would be growth. Could be thickness of stems, could be height of the plant, could be color of the plant. There's tons of different things that could come out of dependent variables, and it's fine to have as many as you want. If you're going to measure all of them and you can make sense of them, go ahead and measure it. It's fine. But when it comes down to independent variables, you really only want 1 or 2 or 3. You want to minimize the number of independent variables, because otherwise you run into an issue where your experiment may not make much sense. Right. It becomes too difficult, and then it's, okay, as I was, if we go back to the space shuttle component testing, as I was pulling on the space shuttle component, I was simultaneously heating it up. Well, I don't have a measurement for when I have a force load of 4,500 pounds on this component at 60 degrees Celsius. I only have a measurement at 4,500 pounds and 450 degrees Celsius. And I know that that behavior is not the same. So I don't really know at that point what I'm even measuring, because it doesn't make sense any longer. Now, it's not data that I can use because I had too many independent variables that were all changing simultaneously. If you want to have multiple independent variables, run multiple independent experiments. Now, there will always be times when you have to have 2 or 3 independent variables because they're so heavily linked together, you can't separate them. That's going to happen. Sad fact of life, you just have to deal with it. It will make your analysis harder. It will make your results more difficult to interpret. You will have to be more careful when you handle those results, and you'll have to make sure explicitly that you state any issues that would have arisen because you had the multiple variables. Okay? Now, there are 2 other kinds of variables. Anybody know what either of those are? Who said that? Yes, control variables. Now, one thing that trips up a lot of people when it comes to control variables is we're controlling the independent variable. But this is called the control variable. But we're controlling this one. What's the difference between the 2?
Control variables and the state the same for
Right. This is a constant variable. This is something that you measure that you are trying not to have impact the dependent variable. You do not want to know how it impacts the dependent variable. In fact, you're measuring it because you know it probably does impact the dependent variable if it changes. But more than that, it is very critical that you measure what the control variables are.
Question.
Yes?
Why would you measure the control variable if it's not going to change?
To make sure it doesn't change. Because that brings in the 4th type of variable. the confounding variable? This is a great question. In this variable, this is an unmeasured variable. I like to use the example of what happens when you water a plant. Okay? You give a first grader the task of doing the scientific method over watering a plant. Okay? They go in, they take 2 plants, they water one a lot, they don't water the other one very much. Both of them die. The first grader then concludes that it doesn't matter how much you water the plants, they're all doomed to mortality. There's a number of variables that weren't taken into account there. Just because the person watered the plant does not mean that the soil humidity changed. Could be that they poured water on and the water seeped off. Could be that they poured water on, the water went all the way through the soil, went into a drip pan. It doesn't matter how much you water if the soil humidity does not change. Similarly, it doesn't matter how much you water if your plants don't get sunlight. Or if one of your plants gets more sunlight than the other, that is going to affect the outcome. It's going to affect the growth. You're no longer just measuring how much water there is. If you're not measuring light intensity too, which should be constant for both, but may not be, if you're not measuring it, that could contribute to error in your system. And it could cause a false reading in your scientific method. The scientific method itself would tell you that you're right. You're doing a great job with your science. Good job. You found water does not matter. All plants are mortal. That's why scientists disagree. Everybody assumes different things. A confounding variable has resulted in a whole lot of really bad science. And
So it's essentially an unprecedented variable, something we didn't think of.
it's something you didn't think of. Yep. If I go back to the example of the watering the plant, it's, if you have one plant's in the shade and the other plant's in the light. Well, the plant in the light's going to dry out faster because it's in the light. The plant in the shade may not grow because it's not getting any light. So how does that impact it? If you're not measuring it, if you don't even care about it, but you're watering both of them diligently, one differently than the other, your results aren't going to matter. It's going to be nonsense. Okay? The goal of a good experiment, of a good scientific method, minimize these, maximize these, and carry as many of these as you can. Minimize this as much as possible to within reason. Again, you brought up the point that it needs to be logical, okay? You shouldn't be measuring whether or not Thor is on another planet fighting somebody, because that probably has no relationship to whether or not your experiment's going to work. If you're measuring solar radiation, you may not need to know what the temperature of your beverage next to you is. That may not be relevant. It's relevant to me, but may not be relevant to you. Very particular about temperatures of my drinks. I cannot drink anything hot, so I can't ever be a coffee guy. Get out of my class.
Have you ever had
I've actually I've only had cups of coffee this year.
I just can't drink coffee. I have tried iced coffee and I don't like the flavor, but dang you, you ruined my argument. Huh?
Have you tried cold?
So anyway, what's that, James?
Have you tried cold brews? They are so much better because they're not made hot. They're made cold over a longer period of time.
Really?
So the acids and everything that are in hot coffee, the acids and the oils, not there.
I have never heard of cold brew coffee before.
So it's
Try it. It's brewing in cold water over the course of like 18 to 24 hours.
Weird. That's probably why I haven't.
Sweet.
I will have to look into that.
So it's like cold brewed tea, but not
Yeah.
that.
Okay. Does anybody have questions on what these 4 types of variables are? We're going to be doing some in-class activities with variables, understanding scientific method in the next 2 weeks. But for right now, I would like to quickly transition. Well, before the video, I need to show you a document. I posted this on Canvas yesterday. This is the project description for the first project for this class. Told you it was coming. It is here. Let me go ahead and switch the live stream over. Yes. So this is where it automatically does that. It's just really cool. But oh well. That was a different class. We've matured since then. We're all older and more wiser. Namaste. Namaste, my friends.
Not by long.
Whoa. Whoa, it's a judgment-free zone. Except I grade all of you.
We've come a long way since the colonoscopy class.
Oh, yes, yes.
Those
Yeah, we really have. Back when we discussed colonoscopies, we have ascended beyond that. We are now into the realm of more mature things. So this is the project description that I have posted on Canvas. Does anybody know what a non-Newtonian fluid is?
Yes, Oobleck is an example of a non-Newtonian fluid.
It's like you. You guys are the ones that answer all the questions. You answered a question too. Good job.
Because we're smarter than everyone else.
Non-Newtonian fluids are just so cool.
Non-Newtonian fluids. What is the definition of a non-Newtonian fluid?
Fill it out or like raise my hand?
Okay.
Fluid that doesn't follow Newton's laws of viscosity.
So what does that mean?
So essentially,
It's a fluid at rest and it's a solid
Oobleck.
with any kind of force.
That's one kind of non-Newtonian fluid.
So would it be like a non-polar, like oil and water? They kind of.
Well, not quite.
Liquid viscosity is susceptible to change.
What does that mean?
It can change.
Yeah, no one agree with definitions.
It doesn't. It does not change at random. It always changes. There is a cause and effect relationship. Now you're getting closer. I'm going to go ahead and take this to an explainable step, though, hopefully. All right. Let's say here's me. I always draw myself with good hair because I'm an optimist. And a smile because I'm an optimist, obviously. I've got great hair. Why not smile? And I'm thin because I'm also an optimist. I'm going to be moving through a body of water. Okay? Does the water just part and let me walk through? I'm not quite Moses. I don't have staff. I got to work a little bit harder. And Moses didn't part the water till apparently after he was 80 years old, so I got a few more years to live. No, this water is going to push, it's going to push back on me as I move through it. The faster I try to move through this water, the harder it's going to be pushing on me. This is why nobody runs underwater, and the people who try get exhausted very quickly. You have to exert a significant amount of power to move in water, especially at higher speeds, because you are forcing the water to flow around you. Okay? That is a measurement of the fluid viscosity. Viscosity is the difficulty, the force required to move through it. And that's kind of a dumb representation, but it's weird. I'm not watching myself again. Except for this time it's not cascading. So I'm just, nice. Look at that back. You could like really see where I'm scratching here. Oh dang, we're regressing.
If you change the camera angle, you can watch yourself watching yourself.
All right, that's a dangerous suggestion. I'm not pointing the camera that way. We're not falling back into this loop. So, in this case, the faster I go, the more force I experience, okay? This is water, which is a Newtonian fluid. As speed increases, force increases proportionally. Okay? Proportionally, that's the key word here. Newtonian fluid, the increase in speed means an increase in force. If I'm going twice as fast, I'm going to experience twice as much force. That's just how it is. It's a Newtonian fluid. Okay? A non-Newtonian fluid has a nonlinear relationship between force and speed. Okay, that does not mean that moving faster will always mean more force. In fact, there are some non-Newtonian fluids where the faster you move through them, the less resistance you experience. And then there are some non-Newtonian fluids, like oobleck, where the faster you move through them, they become substantially harder. The force dramatically increases that it's exerting on you to the point where it feels like a solid, which is really cool. Blood is a non-Newtonian fluid, but it is the opposite of oobleck. It is strain, there's strain thickening, and then there's strain thinning, I believe is the other term. Strain thickening fluids are like oobleck. Strain thinning fluids are like blood, where the faster your heart is pushing blood through your body, if the force were to increase substantially by the speed of blood traveling through your body substantially, your body would tear itself apart. So the fact that blood is a non-Newtonian fluid allows your heart to change the speed at which blood travels through your body without harming the blood vessels. The force increases with increasing speed, but not substantially. It's a very minimal increase. That's why working out is considered good for you, not bad. Don't work out too hard, you'll die.
Not too hard and your blood vessels in your arms.
Only if you get this to go on the bench press.
Oh, yeah. In any case, gonna go back here. What we're dealing with this project is you will be talking about oobleck. Now, again, this is a strain thickening material. There are tons of different types of non-Newtonian fluids. Ketchup is a non-Newtonian fluid. As I mentioned, blood is. Those are the ones that come to my head right off the top of my head, but there's a bunch of them. All it means is that there is not a linear relationship between force and speed. Okay, the power of a non-Newtonian fluid is that it gives you the advantage by which now you can change a system's performance based on how the speed of that system is occurring. So if it's going faster, you can either increase the speed of the force, which would increase frictional forces, which would require a lot more energy to operate, which is kind of a self-regulating system. Or you could decrease speed such that you aren't producing as much heat. Your system automatically adjusts so that now it's not producing as much heat. It doesn't have to do as much work in order to get the same kind of fluid speed to have happen. Okay? So this does allow for higher performance dampers, systems that can handle at extreme speeds, that kind of a thing. What you are going to be doing, you and a partner, you're going to be doing research, studying behavior, and ultimately performing an experiment on a non-Newtonian fluid being oobleck and how it could be used for damping vibrations in systems. Okay? Vibration damping is just how fast things move in a system. One application that has actually been mentioned for oobleck is in earthquake control. For small earthquakes, you don't need a whole lot of force because that would actually cause the top of the building to move. But at very large earthquakes, you may not want the bottom to break free. Because if that happens, it may lose its integrity at the base and come toppling down. You may want it to be a little bit more rigid. So there are tons of applications for non-Newtonian fluids. I would like you to study them. Next week we're going to be doing some research. As far as tasks you're going to have to do, you're going to need to generate a cogent research question that's going to guide your experiment. Okay? You're going to need to come up with an annotated bibliography over your research. You will have to write up your experimental procedure, perform your experiment, and then individually, everyone is going to be writing a paper over this. Okay? We're going to be working on this for the next 6 weeks. So we have time to get all this done. As far as specific timelines and deadlines, next Monday, we will be generating a research question. We will be doing research in class. The culmination of this research will be an annotated bibliography. That's due 3 weeks from Monday. Okay? At some point, I'm going to stop you and we're going to have a professional interview. You will have to dress up for that. That will occur 2 weeks from today. I told you at the beginning of class, I make the students dress up because I like professionalism. This is one of those times. It's going to occur 2 weeks from now. If you do not have clothes, if you cannot perform by that day, I can push it off for you for another day. But you still have to do it. And it's going to suck because we can't do handshaking, and I love handshakes. It's my favorite part of that class. Just have to shake hands with yourself. There you go. Oh, it's just, that's not even professional though.
It isn't like Corona time.
There you go. I'll give everybody gloves. Then we can shake hands.
Everybody gets one latex.
You get one glove. We're Michael Jacksoning this. All right. After you produce an annotated bibliography, which I'm going to give you the guidelines for, you're going to be writing up an experimental procedure. We're then going to be performing an experiment and writing your individual papers. You should be starting on your individual papers about the same time as you're writing your annotated bibliography. The purpose of having an annotated bibliography is to make citing your sources in your paper a lot easier. Should be the background research of your paper. So really you can start working on your paper as soon as you start working on your annotated bibliography. But that said, you still have 6 weeks to finish your final paper, so time is on your side at this point. Okay? Now, as I have said earlier in class, I expect all of you to be adults. You are in this class because you are an adult now. You are not my children. I don't have any children that I know of. I don't have any children. I promise you that. Unless somebody, nope. I was going to say like came in and did some biological research on me, but that did not happen. I do not have any scars. I don't have any kids. You are not my kids. I will not treat you like kids. You showed up in this class, and the day you showed up in this class, I am expecting you to be a professional adult. Okay? You all have that capabilities. All of you are in class today. You're all obviously competent. This isn't a question of competency. Now, adults have adult problems, kids have kid problems. If you miss an assignment because you forgot to turn it in, unfortunately, that is an adult problem. If that happens, the correct adult response is to communicate immediately. Apologize, ask if there's anything to make up, that kind of a thing. Communication is what saves your butt. You say nothing, you fail to hand in a homework assignment, I will assume you're just not going to turn it in. Okay? Your communication is what changes you from being a child to being an adult. Children do not need to communicate because somebody comes to pamper them at some point. I'm not going to wipe your butts. Okay? I will not hold your hand and guide you through this process. You will have to be an adult. You will have to communicate with me. And if you do not communicate with me, I reserve the right to simply refuse your late work. I don't have to accept it. It isn't my fault that you never told me anything. That said, because I am an adult, I'm also reasonable. You shouldn't be afraid of communicating with me. This isn't a whole hand it in on time thing. Yeah, exactly. Duncan's going to throw the elbow. This isn't a fear-mongering attempt to say, turn in your homework on time. This is me saying, I don't care what's going on in your life. Everybody makes mistakes. Everybody misses class every once in a while. You sleep in, you miss a deadline, you're too focused watching The Real Housewives to turn in your homework. You know, it happens, okay? When that happens, communicate. Not if, when. And I will do my best to be understanding. If you're consistently late, you're consistently not turning in your homework, but you're communicating, at that point, I'm going to tell you it's time to be an adult. You got to take responsibility. Again, I expect you to be an adult. If you have a consistent problem, you have to solve that. We spent 2 weeks talking about problem solving. You can't give me that excuse. All right, we're going to watch a quick video. Does anybody watch any videos from Mark Rober?
Yeah,
Love him.
it's great.
This is just a fun video.
Yeah.
We'll watch the Mythbusters one at some point, because that one is also awesome.
The future waits for no one, so we refuse to wait for it. Today, battles are waged in nanoseconds, and planes are piloted from the other side of the world. The future's not coming, it's already here. Join us and be the future.
You can see the force of that explosion transfer right into the table.
Okay, going back to the beginning.
And I'm Mark Rober. Today we're going to be doing a bunch of oobleck experiments, and that's just a mixture of cornstarch and water, which is called a non-Newtonian.
Oh, come on, internet.
Which is basically a substance that, depending on the strain rate, it's either a solid or a liquid, like silicon.
So we're going to find out exactly how tough this stuff is. It can resist a punch, but can it resist a bullet? What about a chainsaw? So for our first oobleck experiment, we're going to cut it with a chainsaw blade. And here's what I think will happen. If the oobleck behaves like a solid, it will get caught in the chainsaw blade and go that way. And if it acts like a liquid, it will just fall straight down, like it's not even affected by the chainsaw blade. All right, here we go. I made it in there because I missed last time. Let's check the high speed.
Okay.
There, boom.
Oh, like it's like shooting out of the bottom.
Oh, there goes the balloon. Oh, it's moving.
It's like dragging it along the chain.
It's shooting it forward. Oh, and then I hit this part too. All right, let's compare that to a water balloon. Mark grabbed the chainsaw and went to action. And you can see that the water did not catch on the chainsaw. In fact, it just fell right through the chainsaw blade like it wasn't even there. For our next test, we're going to shoot a balloon filled with oobleck with a BB gun to see what a sharp, fast, concentrated force does to the oobleck. 3, 2, 1. First, we're shooting the oobleck balloon, and then we're comparing it to a plain old water balloon. Now, do you think that either one of these will be more bulletproof than the others? This is the oobleck balloon, and if you look behind it, the BB actually made it through. You can see it coming out the back right now. That's pretty surprising. I thought the oobleck would definitely stop it. Now it's time for the water balloon. And it looks like the BB got caught, but if you look over to the side, you can see it falling down and hitting the table right there. Then it gets washed away by the tidal wave, and it looks pretty cool. So I tried this again also. I did another water balloon, but with aluminum powder, because I thought it would make a cool color on camera. And you can see the BB flew right through that too, and ended up with a pretty ugly color. Anyway. Okay, so we saw how the oobleck would react to a small, high-velocity projectile. It concentrates a lot of force in a small area. Now, we're going to see how the oobleck reacts to a large, blunt force for my golf ball cannon. Mark, can you turn this off? Nope. You ready for the boondockie? No, you gotta wear them on your ears. And 3, 2, 1.
Don't you hate to be this guy's next door neighbor?
I don't even know where the golf ball went. So here it comes. Out of the gun. No!
Oh my
Look at that!
gosh!
Definitely acted like a solid.
Yeah, for sure. That isn't because it's like chunks.
Yeah, just shattered it.
Dude, the first couple seconds of impact are like, it looks like something out of Star Wars or just like some special, just like
the outside shooting. The outside
like that first shot, it's like spin like that. Like looks like little lightning spindles.
It's almost a pattern, like it's from the golf ball's dimples. That
Oh yeah,
come out that
you're
way.
right. That is one of the craziest things I've ever seen.
All right, now it's time for the water balloon. This propane cannon can shoot a golf ball at over 300 feet per second, which gives it the same impact energy as a .38 Special. And while I've got this propane rifle and a high-speed camera, we might as well see what happens when I shoot it in a watermelon. 2, 1. I think it's safe to say that this watermelon didn't stand a chance. That golf ball went right through it like a golf ball through a watermelon. And this isn't an advertisement for Fresca, but I mean, if you guys want to send me some, that's okay too. Luckily, none of this watermelon went to waste. You want some watermelon? In this oobleck balloon, I put a firecracker on the inside of it so we can see the explosion from the inside out and see what happens. Will it contain the explosion, or will it just burst right through like nothing was even there? Let's find out. 3, 2, 1.
This is bad.
You can see the force of that explosion transfer right into the table, and the whole thing, made of solid wood, starts wobbling. And then it sprays this oobleck everywhere. I'm covered. Completely covered. Everything is covered in oobleck. So while we were out here filming the oobleck videos, we also filmed some videos for Mark's channel.
So we had 2 grenades. One fell in the pool and one stayed on the pool deck. One of us jumped in the pool and one of us stayed on land.
If you want to see who survived in his video,
And the science as to why they survived.
so click this here and check the link out in the video description. It'll take you to the video, and check out his channel while you're at it. He's got a bunch of really cool ideas and science explanations, so we'll see you there. Wait, this was a prop grenade, right?
I didn't like
Alright guys, thanks again for watching this video.
Okay. We'll watch the Mythbusters video at some point too, because that one's pretty awesome. Anybody seen the Black Mythbusters video?
Yeah, they start running across it.
Yeah, it's pretty. You got a quiz on